All right. So, Moein, are you hearing me now?
Yeah, everything
Perfect.
seems
Hi to
fine
you.
here.
How are you today?
I'm doing great. How are you?
Doing good, thank you. So, let me also say hi to those who are watching us. My
Yeah,
name is
hello.
Pouria, and this is Moein. Let us briefly introduce ourselves in the first place. So, my full name is Pouria Ruzroch. I'm originally from Iran. I'm a medical doctor, currently here in the United States, Connecticut. I'm about to start my radiology residency at Yale University, and previously I have had a chance to be a data scientist and a researcher in AI at Mayo Clinic for about 4 to 5 years. So, that period of time actually helped me grow a lot of interest in AI, and that is basically what we are going to talk with you about today. Moin, do you want to also introduce yourself?
Yeah, I'm Moein, and I'm a final year medical student doing my internship at Tehran University of Medical Sciences in Tehran, Iran. And I've also been doing AI research from 4 years ago, and also doing some freelancing AI projects as a machine learning developer, which I currently do as a part-time job. And yeah, here I am.
Perfect. Thank you, Moin. So, just a very brief introduction. So, Moin and I used to have these kind of meetings, the first of which you're going to watch today, with each other for about past 5 or 6 months, I believe. So, every 2 or 3 weeks, now Moin and I just sat together and talked about the new things in AI, the new updates, the new, exciting news or whatever that came out since the last time that we spoke together. And we used to share those kind of updates with each other. And we found that to be quite useful. We found that to make us more passionate in the kind of research that we were doing. We found out to be kind of a source of inspiration for keep doing what we have been doing so far. So after a while, we thought that, why not to just share these meetings that we have with each other with everybody? We are not quite sure if anyone is going to watch this, to be honest with you. Neither Moeen nor I are professional YouTubers. We are not professional video editors. So you probably are not going to see anything fancy from a video editing standpoint here, but we just wanted to share what he and I have been trying to have among ourselves and really enjoyed that, and then see if you guys are also going to enjoy it or not. And if things go very well and people like this, then we might think of making that a little bit more professional, adding more components to that. But for now, what you're going to see is basically one of the meetings that Moin and I have every now and then with each other to share whatever interesting things we find in AI. Moin, do you want to add anything to that, or shall we just jump into it?
No, I think yeah, you covered everything, and just quick mention that these are not going to be in-depth tutorials or I don't know, educational material on any of the topics we touch on. You can just look into this session as an introductory to some topics to just bring them on your radar so that you may want to follow them. And we are also not experts in many of these topics, and we are trying to learn. And this way, we wanted to share what we learned with each other so that we kind of parallelize the whole system. And this is the first time we're recording this, so there could be many things can go wrong. So please bear with us, and let's see how it goes.
Perfect, thank you. Yeah. And one last point. So, Moin and I don't have a clear boundary on what kind of topics we are going to review or what kind of topics we are going to exclude, because both of us have kind of roots in medicine and healthcare. So we will probably have kind of a special eye on whatever comes up in the world of medicine AI or medical AI. But apart from that, we might cover everything from the engineering world to the medical world and beyond this. So basically, we just are going to share whatever we found interesting and thought that the other person might also find it useful. So I guess if we just start and go through it, everybody will understand how we do these sessions. And we usually switch turns when we are going to go through these meetings. One of us starts and share a couple of articles, blog posts, or whatever they have found and talk about that, and the others tries to listen and ask questions, and then we switch places. So this might happen a couple of times till the end of the video, and we usually do this until we are out of newer things to share. So this is not going to be a very short video. It's going to take probably more than an hour, or maybe 1.5 hours, but hopefully all of that is going to be useful to you. So
Yeah,
Moin,
definitely.
yeah,
So.
if you agree, I guess maybe you can start and then I can follow after you, and let's jump into it.
Yeah, sure. Let me share my screen here.
And before you share, so just to remind
Yeah.
everybody, we're currently on January 16th. Oh yeah, and it reminded me that I probably need to
Uh, yeah.
um, share.
Allow me to share my screen. Yeah.
Just give me 1 second. All right. So hopefully you should be able to share it now. Are you able to do so?
Yes. Yeah.
Yeah. So today is January 16th, and we are going to share this episode. So whatever that we are going to talk about has been published, most likely before this date. All right, Moein, I'm
Okay.
all ears. You go ahead.
Can you see my screen
Yes,
here?
I can see that. I can see that.
Yeah. Okay. So this is a paper from April 2024. Eyes Wide Shut, and it is by New York University, FAIR, and FAIR Meta, and also the UC Berkeley. And you see this special name here, so
Yeah.
you could expect some interesting content
Mhm.
from this. And I recently saw this, and I was wondering why I hadn't seen this earlier. But this is a really interesting perspective on how the VLMs work, what are the kind of bugs in how they understand or at least process the natural images and text, and what are the shortcomings and how we can improve upon them. Basically, I try to zoom in a bit so that you can see the figure here. This is the main figure that brings up the main weakness that this paper is about these VLMs. And that is the hallucination of some of the details of these images when asked some specific questions about them, and also how easily they can answer some basic questions that are very easy to humanize to in a wrong way and hallucinate things. So as you can see in this image, in this figure, there's a simple question: how many wheels can you see in this image? And the VLM answers 2 wheels.
Hmm.
Or this one, as you can see, the door is open, but the VLM cannot detect that. And they wonder actually, why is this happening? Why these VLMs cannot comprehend or understand these simple things that are so easy for human eyes, but this is so problematic, seemingly for VLMs. And they contribute this with a theory, or as they suggested, to the clip module of these VLMs. As you know, most of these VLMs are constructed in a way that the image is first given to a clip-like module, and
Mhm.
then the tokens are concatenated to the text tokens, and then all of them go to an LLM, and those image tokens are processed in a way that text tokens are. So they contribute this problem to CLIP, and also they show how this can happen. Um, as you can see here, they do a fun experiment. I mean, they actually base their theory on this, but this is something I think really understandable. They argue that there are images, or to be more specific, there are pair of images that are very similar in the clip embedding space, but they're actually not the same thing. Or there are some nuances in them that clip is blind to actually, and they name it clip blind pairs.
Okay.
If you can see this image here,
Yeah.
there are two dogs here, but the dog on the left has a different position in these two images. The clip model, according to its embedding space, says that these two images are really the same or similar to each other. But if you encode these images with a different model called Dino, which was another self-supervised model, which again from the Meta lab that learned very fine-grained representations of images, to the eyes of these Dino model, these two images are not that close. So they go make a pipeline like this, and from a data set of, I think the Lion data set, if I pronounce it correctly, they choose a subsample and then select some pairs that are close in clip embedding space, but far from in the dyno space. And these are mostly images like this one. I think you can in this figure. Yeah, these are mostly images in these teams. They're really the same object or very similar objects or animals or humans, but they're different in position or in the orientation. And they actually, I think they provide the list. Yeah, they identify 9 visual patterns that these clip blind pairs have. And these differences that clip is blind to, but Dino and some other like masked autoencoder, I think, self-supervised models are not blind to, are some of these 9 categories. And it's interesting that these categories are LLM generated. And I really encourage you to read the paper because it's a
Wow.
really interesting one. Yeah, and they identify these categories like when the orientation of the object is different, they look the same to the clip and also to the VLM that is based upon clip, but they are not actually the same. And if you ask nuanced and detailed questions about the image, the VLM actually sees them the same, so it can't differentiate them. Or the state or condition, and there are very good figures in this paper that provides example for each of these uh, actually categories. And also, clip is blind to text, which is something that many people may ask about VLMs. But you might wonder, okay, ChatGPT and the newest VLMs are really capable to do OCR and reading text. Remember that this paper is for a few months back, and at the time, um, most of the models that they analyzed were not good at this. And also, some of these tasks are could be improved with fine tuning specifically on those pairs. So these are some basic and general categories. And they built some pairs like this, and they actually propose a new benchmark called MMVP, which stands for here for multimodal visual patterns. And this benchmark and dataset actually is mostly these pairs that are blind to clip features, but they're actually different images, and there are many details that differ in the two. And they evaluate the models at the time on this benchmark. And here are the results a few months back. To the human, these pairs are easily differentiable, and the questions to those images are easy to answer, so humans do perfect on them. But Gemini and GPT-4V, GPT-4o wasn't available at the time, are doing not very good on this. As you see, the random guess is 25%, so they weren't doing very fine, very good. So, but the current models are doing much better on this. And
And
the other open
yeah,
source models are really even below the random guess thresholds.
yeah, that's really funny. You know, how can a model actually, I mean, this clearly shows that some models systematically do this wrong. You know, it's not
Yeah,
systematically doing it right, systematically doing it wrong.
exactly. And yeah, so this was the first paper I wanted to introduce. There are a lot more interesting things into this paper, how they um, formulated the question and how they actually came up with a solution or at least a benchmark for evaluating it. I think this is a very good to read paper for junior researchers to see how they can approach a problem and how they can propose some solution. If you cannot solve the problem uh, um, in one paper, you can at least propose a benchmark or metric how to measure it. And I really like the idea. And yeah, I think they bring up a really important point on how these VLMs could be blind to simple things.
Yeah, it is a quite an interesting paper. So two things regarding Yann LeCun for those who might not know him very well. So first of all, he's one of those very big names in the world of AI, and he's very famous for two things. First thing is that he's one of those advocates who really doesn't think that the current generation of LLMs and VLMs are going to lead us to AGI or artificial general intelligence. He really thinks that these models have some very significant shortcomings that probably they have their own use cases in his eyes, but he thinks that these models cannot lead us to AGI. The second thing is that he is very much invested in developing self-supervised kind of models, like this Dino V2 or models like that. So it kind of makes sense, looking at Yann LeCun, this kind of papers coming out that highlights the shortcomings of LLMs, very rightfully in this case, and then advocating for how the self-supervised learning part of these models could be done in a better and more improved way. So very interesting paper. Thank you for sharing that. I'm certainly going to read this one.
Yeah, and I hope the audience also like this. Okay, I introduce another one, and then I probably give it to you, and then we switch back and forth.
Yep.
So the next one, I hope you're still seeing my um, yeah, BIOMEDICA, which I saw this actually a few hours ago on X
Yeah.
first, and then went through the um, details of it, and I was getting more and more impressed how as I read more about it. It's actually a very huge data set, and it's a work by Stanford
Yeah.
researchers, and this is the paper. And I still haven't gone through the paper, but the website also had great details on how they made this and how useful this could be to the community. This is actually a data set of the entirety of the PubMed Central Open Access, which is a crazy idea that they have done that. And this is a 27 terabytes of data actually, but they say how they train models on it, and this is cool too. And basically they scrape the whole PubMed, and there are of course papers in there, and PubMed is a kind of like where we search for medical, and this is an actually index search engine, kind of like for biomedical literature, and they script it, and there are lots of papers with figures in them, and this is a great resource for training kind of like contrastive models like CLIP that require paired images and text. And there are references to each figure in each paper. So those references could act as a caption like or related text for each of these figures. And also, let me see. Yeah, and they introduced lots of different filtering methods that I'm still about to read, and I'm not going to dive into that because I still haven't read them. But they first scrape this and then do something cool, kind of like an unsupervised clustering using Dino features again. So it's the second time Dino V2 is mentioned here, and this is kind of random. And they first get all of these visual features and do some clustering on it using PCA and K-means, and they in this unsupervised manner, they classify them, cluster them into 17 global concepts that I'm going to show you the clusters down below, and also a bit more local concepts. And as you see here, there are 24 million image captions, 30 million figure references, and lots of crazy numbers here. And they go on and train clip models on these paired images, and they also fine-tune these clip models. And they show that the zero-shot performance of all of these clip models are the state of the art now and beating the previous state of the art, which is again another good news. And these clip models could be used in the further VLMs. I'm thinking out. I'm thinking out loud. I'm not sure even they tried this or not in this paper, but these clip models could simply be added to VLMs. And then, as we discussed in the previous paper, the models built the VLMs that contain such clip models should be performing better on biomedical data and question answering regarding those data. And you can see some of the categories and some of the images here. As you see, that unsupervised clustering seems to be working very well here. All of these three are clinical imaging data that I think they seem fair to me. Maybe not ECGs, but these two are definitely clinical imaging data. And the local taxonomy also seems fair. And there are lots of other plots and charts and chemical structures, and these are all available. As far as I read, these are publicly available to everyone. I'm not sure about the license, but it was very interesting that they are open sourcing all of this.
Yeah.
And yeah, and here you can see the results of the final clip models on the some of the radiology data sets like this chest X-ray. And as you can see, these are zero shots. So at the first three are zero shots clip models. So the clip model is not fine-tuned or another classifier is not added to this clip model. And only by capturing the similarity of the image representations or embeddings to, for example, 10 classes as a text, the embedding of those texts to this embedding of image, they do this kind of like zero shot classification and the pair with the maximum similarity among those, for example, 100 classes gets classified as that class. So this in this zero shot manner, you can do classification on every classification data set for free, kind of, and you don't need to train a classifier on it. But if you do train a classifier, as you can see here, you will get a big jump.
Yeah.
And this is a very promising point here, that these models at least could serve as a good pre-trained model, or as I mentioned before, as a good module to be added to VLMs, because they contain probably a lot of information about biomedical concepts, and they should generalize well. And yeah, this was another interesting recent work that I saw. Just to mention that these links will be provided to the audience, so we will probably put this in the caption of the videos or send the audience in a way that we will figure out in the next meetings. But yeah, um, I think this is it. What do you think about it? I think you wanted to mention this, yes?
Actually, you
Based
caught
on
me.
your first reaction.
This was one of the two papers regarding embeddings that I wanted to share, but I'm very happy that you mentioned one of those because now I can spend more time on the other. So first of all, this is quite an impressive paper. I also went through that a little bit, and I was impressed, as you mentioned, by the size of the data set they used to train this model. I mean, it's huge. And not sure if
Yeah,
you noted that, Moein, but basically they also talk about how they train their model, and they use the term
yeah,
streaming rather than downloading the entire data. They say that we didn't download the data, so we basically streamed the data and then trained our model on it, which is, I guess, a very interesting idea. I mean, streaming basically enables you to train your model on a very huge data set without needing to first bring that data down and then, to your local compute and then try to pre-process it and then train it. So the entire training pipeline was also very impressive to me. But yeah, I mean these embedding models, in my opinion, have always been the connecting piece between generative AI and discriminative AI. Because when you have those, then you can, as you mentioned, fine-tune them to be a classifier, to be a segmentation model, to be whatever that we want to use for the discriminative purposes. And then at the same time, we could also, use them, as you mentioned in the first paper, to train a VLM or another generative AI model. So embedding models are quite interesting topic to me. And the whole idea is that you just realize and you just figure out a way to embed or to compress some very semantically complex kind of information into a vector that is relatively very short in size compared to the original data that it comes from. Just imagine a CAT scan, CT scan of, I don't know, maybe 512 by 512 pixels, and then it could have easily 40, 50, 60 kind of Excel slices. And this volume of data, you just compress that into maybe one vector of size 1024, 2048, 1496, whatever. And then these 2000 values are going to have some patterns within them that these models can pick that up. And then they can use those patterns to do a lot of classifications down there, from not only from the modality perspective, but pathology perspective, anatomy perspective. So I guess embedding models discussions is kind of very interesting. And I want also to highlight again that we saw Dino V2 there, which I
Yeah.
guess shows the power of that model in learning self-supervised. I guess the model itself is a variant of Dino V2, right? They basically fine-tuned Dino V2 on this entire section. Am I right?
I'm not sure they're fine-tuning Dino. As far as I know, they used their Dino features on the images
Okay.
to first classify them in broad concepts.
Huh?
And then experts went through these unsupervised clusters to see if they make sense or not. And then after this clustering, which is kind of like a metadata for the pairs here,
Yeah.
they're not probably necessary for training the clips in the next step, but these work as a good kind of metadata for researchers to maybe who want to just download just one part of it, not
I
going
see.
through all of it. So I think this is a previous step, like as they mentioned here in the transform step before going to the training. And when they want to train the contrastive self-supervised model, they use clip. This is not Dino. And yeah, and also they train many different versions of clip with different filterings. They mention it in depth in the paper, as I was saying, and there are also these different versions of clip mentioned in the tables that I showed you, these CB and CF. That I didn't have the time to go through them because I just found this paper. But yeah, I think this is another great resource for the audience if they want to go through.
Sure. So now I think I understand it better. So the way that they used Dino was to basically do an unsupervised clustering of the image or figure caption pairs. And I guess that kind of makes sense for the process of data handling because they're saying that, if there are some figure caption pairs that do not fall into one of these major categories, then maybe a human being could manually go and check them because maybe something could go wrong with those. Maybe there is no figure in that. Maybe this is just an error from the journal's side, the figure is not loaded or things like that. Now I guess I understand why they use that. They basically wanted to curate their data. So now they are safely saying that if we are including some training data for our downstream clip model, the figure caption per in that data belongs to one of these 17 large categories. So basically we are sure that it is a high quality kind of image caption per that now we are using that for training the clip model. Does that make sense?
Yeah. And also I wanted to add that these clusters do not come with names or
Yeah.
predefined concepts because
Yeah.
the clustering just says, okay, these images are close together, these images are close together, but far from those group. And these experts going through these clusters could actually name them, could actually give concepts to them.
Mhm.
So these names here, like clinical imaging data, or microscopy or immunoassays. These are names that those experts panel assigned to these clusters. And some of them make sense, some of them maybe not a lot, but at least um, they mostly make sense.
Yeah.
And then they went down to each of these clusters and then did this clustering again, and then they came up with this local taxonomy. So yeah, this was actually how they clustered this. And they're probably very good to use cases for these clusters. Like as I said, probably when someone wants to only download and work on the X-rays, they can directly go to them and don't have to download this huge data set. But I'm not sure how else they use these categories in the paper.
Yeah, regardless, very interesting paper. Thank you. And if you don't mind, I can maybe follow up on these and then try to share something that is very similar.
Yeah,
So let
sure.
me share my screen now. Are you seeing my screen?
Yes.
All right, perfect. So let me just make it a little bit larger. So I'm going to introduce another paper, which is very similar to the one that you just mentioned, Moein. It's named MedImageInsight. It's another embedding model, this time coming up from Microsoft. So it seems that all these, universities, big tech companies are getting more and more involved into medicine, which is both very nice and scary at the same time. But basically, so this is quite a similar paper. So this team are mostly from Microsoft, and we see some people, with dual affiliation. Dr. Longren, for example, I know that he has already been in Stanford. So people, just circulate between these big names, Stanford, Microsoft, from academia or industry side. And they are presenting something quite similar. So they talk about MedImageInsight, and MedImageInsight is another model that basically they train, unsupervisedly, and it kind of is a clip-like model. Basically, it can help to get some embedding out of some imaging data, and then someone can use it for classification purposes, for downstream kind of supervised model training, or even use that for image generation. And the way that it is different from the previous paper is that this time they didn't show figures from scientific articles. They basically trained this model on a collection of basically real medical imaging. So it was trained on medical images with associated text and labels across a diverse collection of domains, including X-ray, CT, MR, dermoscopy, OCD, fundus photography, ultrasound, histopathology, and mammography. So basically a very large collection of different medical modalities, medical imaging modalities. And this is nice. And again, what they say is that, when we train this model, then we show that it is going to achieve the state of the art, or at least the human expert level performance across classification, image to image search, and fine tuning tasks. And then they, compare this with some state of the art models, GPT-4o, for example, and they show that their model is better than GPT-4o. And this is interesting. It says that, it outperforms GPT-4o in kind of clinical metrics, but underperforms on lexical metrics, which lexical, correct me if I'm wrong, is basically mostly talking about how good of a word choice the model has had, how good linguistically it can be. This is my very raw understanding of lexical. But the thing that probably matters the most to people is this clinical metrics, and their models are actually better. So let's also talk about some figures here. I'm not going to deep dive into details of these papers because I think that this is something that people can read on their own, but to simply just give a general understanding of the paper. So again, as you see here, they are talking about their models compared to some other models that have been out there. And some of these models you probably would also see on, the tables that the BIOMEDICA paper had. And it could be interesting if some people can basically compare these two together, and I'm pretty much sure that this is going to happen very soon. But these two papers actually came out very close to each other, so I would be surprised if they have, if they could actively compare against each other. But again, the kind of comparisons are similar. First of all, you see that MedImageInsight has a very low parameter size, which makes it a valuable tool because, if the parameter size is too large, then you might not be able to use the model for some use cases. It's a multi-domain model. It is pre-trained on text and images as well, pre-trained on labels. It could work for, image-to-image classification, 3D purposes, generative purposes, a lot of things. And then they also have some nice figures here that I guess will summarize the entire paper. Let me zoom in a little bit. So this is showing the kind of data sets that they use for training their model. Again, the huge difference here between this paper and the paper that Moein shared is that this one is trained on actual medical imaging data sets that come up with text labels. For example, you see the famous mimic chest X-ray data set here, and they have some, studies from the MRI data set, CT data set, TCGA, I believe, are some of the largest data sets out there on MRI and CT. And they basically collected as many of these as they could and then put those together, train the model on that, similar how to the previous paper did. And then they are showing their kind of performance compared to the previous models. And you see that when you look at the model size that it has, it's quite an impressive performance, right? And then again, when you scroll down, you see the classification performance of these models compared to other ones. And This is maybe even using a very, very simple kind of classifier, even conventional machine learning classifier like k-nearest neighbor. The model, the embeddings are so rich that even a KNN classifier could basically do a very decent job in classifying most of the things. And they compare their model against Biomed Clip, Biomed GPT, and then MedFlamingo. These are the three of those famous clip-like models that had come previously on medical world. And again, they are showing how superior their model is. And then obviously you can just use this kind of model for generating reports. So it receives this kind of X-ray as an input, and then it predicts some image findings out of that. And then, so these models are not perfect. Definitely some missing parts are gonna be there, but even the fact that they can come up this close to what a radiologist could basically have reported for this imaging is fascinating. And then classification examples as well. So basically the model can say that, this is a dermatology image, and I believe down the road they were also talking about how it could predict what kind of pathology it is there. And again, some very nice comprehensive evaluation of their model across various data sets. And if you look at the color coding here, basically the color coding is talking about the green exceeds human expert, yellow SOTA equivalent or better, and blue still AUC more than 0.9. So very impressive performance. And then let's see if we can find, yeah, this was the paper that I was referring to. So you see that it's very interesting because they use an image. This is kind of an image-to-image classification. They query one kind of an image, and their model finds out other images in their data set similar to this one. So say, for example, you have a photograph of a dermal lesion that is basal cell carcinoma. And then if you just pass this image as an input query to this model, then it can, figure out, I mean, based on the embeddings of this model, a simple classifier model could figure out the other images that are very close in semantic space to your queried image. So basically, it could show to you the other basal cell carcinomas that have been in their validation set. And this is based on their validation set. Now, this is very interesting because now, if you have such a data set, then you can easily think of, say, for example, putting together a collection of 100 different types of BCC that you have already diagnosed in your institute, and then always, query whatever dermal and whatever photographs that you have from your new patients with some dermal lesions using those 100 query images, and then take the average, and if the average is above a certain threshold, label that lesion as a BCC, and then you will have a very good and accurate system for understanding, what these lesions are about even before getting the pathology. So I guess it's very impressive. Again, very long paper, very detailed paper. I believe their model was supposed to be out, and I believe it's public, but it's on Microsoft Azure. So one thing that I did was that I basically just searched for that, and I believe there is a data set from this paper. I'm not sure if this is the official data set, but something that probably has been cloned from their own data, and now it's on Hugging Face. And the code is there like any other Hugging Face model. You can simply download that, and then afterward, just train a classifier very nicely on that, as you can see here, and then load the model, use it for decoding, your own kind of images, and then providing some labels to that. So the model is right now out there. You could just easily play with that, download it for your own use cases, and see how powerful it is. So I pause here. Moein,
Yeah,
do you have any comments or things to share about this?
yeah, amazing. And when you were talking about this, a few topics came to my mind. First, that I'm not sure if you're familiar with the Phi series of models
Mhm.
from
Yep.
Microsoft.
PHI,
That's
right?
Yeah, PHI, yeah. And they're well known for, if I'm not mistaken, for that they are actually smaller large language models compared to other
Yeah,
LLMs, but they are trained on much cleaner data sets,
yeah,
basically made of textbooks, clean textbooks, high quality text. And I'm seeing a similar trend here also. They went for training on very high quality data sets. They didn't just download any data set from the, any unclean or fine-tuned or trimmed data set from the internet and then just train on it.
Mhm.
They specifically went for highly curated data sets.
Yeah.
And I think the performance of their model is maybe or most probably is this good with this low number of parameters compared to other models, probably because of this, or this is probably one of the main contributors. I'm not sure if you agree
No, I
with
totally
this.
agree. So I think that Moein, a pattern that people knew, at least since the time that I came into the world of AI 5 or 6 years ago, and I know that people have been talking about that. And every new generation of the models that come out, people start to think that maybe this kind of obsession is not important anymore. But then again, we figure that it's very important, and that's the quality of the training data. So if you're training on a very, very, very huge data set, even if you are training an LLM like today's kind of LLM generation on the entire as a data set as big as the entire data available on the internet, there is still a point and there is still huge benefits hidden in just curating that data and making it better. And I guess, again, back to the paper you presented, they basically leveraged another deep learning model, a powerful model as good as Dino, to just curate their data. And then the team from Microsoft just did that with MedImageInsight. And I'm pretty much sure that many other people have also reached to the same conclusion that the quality of the training data matter more than the quantity of that. Yes, the size matters on training data set. But the point is that what matters probably more than the size is that how much of a good quality data you have collected there. And I guess these models are clearly showing that. And if you have such a good model, such a good training data, then you can end up with models that do not have that many count of parameters, not that large, not that huge, still very capable in doing the things that larger models cannot do that good.
Yeah, I really like this trend that is being seen in the works from Microsoft because those five models are from Microsoft, and this one is at least from a few authors from Microsoft. And I think the trend in AI has always been like this, that first a new architecture or a new way of training comes up and gets very famous and popular.
Mhm.
And then people go scaling it as much as they
Yeah,
can. Lots of parameters, throwing lots of compute at it and see how it works.
yeah,
And yeah, of course, if you, as we've all seen in the AI, if you throw more compute at it, it probably works better. But if you do that and also work on your data, clean it, and just get a much more high quality data, the increase will be synergistic and kind of like
I agree.
um, X folds, and it will blow everyone's minds out. And I think after a while that companies go throwing computation at their models, making them bigger, they they then come back to curating the data set and see how much more
They can improve it.
intelligence they can make from the same data. So yeah, and I think we are at those times that the importance of data is being much more prominent now.
Yeah, I agree. And it's coming to medical world as well. All right. So speaking of medical world, let me quickly introduce another paper and then pass the ball back to you. So let me share my screen again. Let's go through another paper and then make the screen a little bit larger. Are you seeing the paper now?
Yes.
All right. So this is one of the papers that I really liked. So it's called Foundation Model of ECG Diagnosis, Diagnostic and Explanations of Any Form and Rhythm on ECG. So ECG, obviously, people who are watching us, I guess most of them are from the medical world, so they know that this stands for electrocardiograph. It's one of the easiest modalities to obtain from anyone who comes with any sort of cardiologic concerns or symptoms. This is the one that we do in our EDs, and we understand what kind of serious pathologies people might have. Some of those that might be very time sensitive, like an MI or myocardial infarction. So this is a nice paper. It came out, I guess, a little while ago, not that far, maybe 2 weeks ago, which in the world of AI, depending on how much closely you are looking at it, could be too long. But 2 weeks ago, and then Cell Reports Medicine was the journal that published that. And it basically talks about a signal language architecture based ECG foundation model. So it talks about a foundation model to diagnose the kind of pathologies that are present in an input EKG. And this is something that is very nice. It comes out from Shanghai, if I'm not wrong, from China. So Department of Cardiology, Shanghai First People's Hospital, and then it comes from China. So as the name implies, they propose a knowledge-enhanced electrocardiogram diagnosis foundation model that utilize large language models to incorporate domain-specific knowledge of ECG signals. They train that on 800,000 ECGs from nearly 160,000 unique patients. And this is an interesting number. I mean, 800,000 ECGs, 800,000 is basically a data set that takes years to collect, okay? This is not something that you can easily collect. It's a very huge data set when you look at it from a standpoint that these people come, from medical background, and collecting such a data set itself needs a lot of credit to the authors. And then what they do is that they basically come up with a model that at the end of the day, when the model is trained, they basically can ask it to can just show it an EKG like this, and then ask it a question like, can atrial fibrillation, premature atrial contraction, or premature ventricular contraction be detected on this ECG? So basically, just throw some names, some relatively complicated. I mean, not about AF, but some other complicated cardiac diagnosis or names to the model, and then ask the model to see if those are present on this input EKG or not. And the way that it is trained, it's very interesting. So they basically train it on, again, pairs of EKG images and the reports that we have as ground truth data for those EKGs. So they first get the EKG, they try to encode that, and by encoding, as we have been talking about in the past 2 or 3 papers, basically means that now we are going to compress all the semantic information in that image into some, in maybe a linear vector of not a very large size. Just imagine if we had, for example, 1024 blue squares here, this basically means that a vector of size 1024. And then they kind of do the same with the labels. So it seems that they try to get the original report, pre-process that, or as they mentioned, augment that somehow, maybe add some additional information to that. And then they encode it using now an encoder that is, specialized to encode textual data. And then at the end of the day, when they have the encodings coming out of the record, the encodings coming out of the ECG signal, they just try to basically match these two sets of encoding using a specific kind of loss function. And then when it is done, then basically means that whenever you give an input image to the model, the model, sorry. So basically this kind of information is kind of injected into another network that is kind of a classifier here. So basically they also have some predetermined labels, which is a finite set of labels that we can diagnose on ECG. They also encode those labels, and then they provide the key labels here, the possible labels, the ones that come from the image itself, the ones that come from the report itself, and then they train a classifier on top of that. Okay. And then when the time comes up for the actual inference, again, the EKG is done and it is encoded. All the possible labels are encoded similar to training, and then the model is going to come up with those labels that were kind of present, or with the report that the model is expected to generate for this EKG. So it's kind of both a discriminative and a generative model at the same time. It generates some, report for the EKGs, as well as put some diagnosis on top of that. Again, the details of how they train that might not be the focus of the topic here, but they basically talk about their data set, how many of different labels they had. And as you can see here, as we always see with medical data, the number of negative scans or negative images that we have without any significant pathology are quite significant. But the entire art is in how you are going to curate these positive labels and how you are going to train your model on that. And again, a long paper with many different analyses, but very impressive kind of results. And they basically show how good their models are. I'm trying to see if I remember one of these papers that was very nice in diagnosing the performance, in showcasing the performance of the model. Yeah, so this one, for example, they just provide an EKG of a ventricular premature complex to the model, and then it comes up with some explanations of how this can be diagnosed. And, because the model has been trained on actual reports, now it can be Yeah, it can basically not only detect pathologies, but provide you with clues on how to detect those pathologies. So it's kind of an educational model as well if you are learning about EKGs. And very nice study. Moin, I know that I also shared this with you. So if you have any additional insights on this one and things that we can share with everybody here, please go ahead.
Um, I mean, one of the things that comes, I think, repeatedly in our papers that we're sharing is that uh, I'm thinking that the era of narrow models is coming to an end,
Yeah,
and we are seeing that these huge foundational models, or sometimes they call LLMs and VLMs based on the context, are really going to change everything. And this is, to be honest, one of the greatest sources of stress in AI research these
yeah,
days. Even if you're working in the big companies, I think, and I'm going to share something about this topic after we switch. And yeah, I mean, I remember the first years, like 2019, 2020, that still narrow models that we could train and fine tune on a small scale data sets were still relevant and they were doing good. But with coming of with the age of these foundational models, I think now thinking of training narrow models is a bit short-sighted
yeah,
when you can have access to these huge models that can give you very high quality initial embeddings to then train models on.
mm,
It is really kind of like pointless to train
yeah,
small models. Maybe there are some, of course, there are some use cases for them still, in net in some domains that you cannot use these foundational models, or these foundational models do not represent the data well. But I think this is temporary, and in a few years, or maybe in a few months, as everyone's just using these huge models to get embeddings from and then start from there. And this really makes it really hard, I think,
yeah,
these days to be doing AI research
yeah,
and not to be disappointed when you see these huge data sets that you cannot, of course, work on them on your personal computer at home. You
yeah.
need to have access to huge GPU servers in the cloud. Yeah, and this is one of my personal sources of stress, and I'm not sure how you're feeling and dealing with this.
Yeah. So kind of similar. So I totally agree with you that the landscape of narrow focused deep learning models are becoming smaller and smaller as we go forward. I still think that some people might need those narrow focused models, specifically if they are dealing with very specialized kind of use cases that probably nobody else in the world has. Maybe somebody is working in an institute, and within that institute, they need a certain use case of a model, and it still can be a very small deep learning model that could be trained on their own data and then applied, or maybe just a fine-tuned version of these larger scale models. But I guess for most of the use cases, that we have in not only medical world, but probably many other worlds as well, these models are becoming so and so powerful that their zero-shot capabilities, or maybe few-shot capabilities, will exceed any kind of fine-tuning or alignment that people might do in-house. Yet, so regarding how I am dealing with this stress, first of all, it's really stressful. I agree. The reason for stress is that as a researcher, you might be more passionate about, going all in and trying to develop your own deep learning model. And I still feel very good when I look back on those days that I was developing these models at Mayo. The thing is, I guess if that lifetime is coming to an end, a new lifetime will start, and this new one is probably more focused on product engineering rather than on ML development. So basically, now that everybody has access to these great models, coming from these big names, now the real question is that are you a problem solver at the end of the day or not? I mean, are you capable of just getting one of these models and solving the problem that you or your institution or organization is facing with as cheapest solution as possible, or with as most cost-effective solution as possible. And that's something that will probably set people apart, set researchers apart, set developers apart. Uh, yeah, that's my way of thinking about that. And then I'm obviously personally moving more towards learning, things about how to deploy how to better incorporate these models into practice, and then maybe learn a little bit more about UI development, UX, product engineering, MLOps, things like that. I guess those are gonna be nowadays more important compared to just, the art of developing deep learning models. That still is gonna be very relevant, but probably mostly if you're working in one of those big companies that have access to those huge GPU clusters that can train these models on.
Yeah, definitely. And also, wanted to mention one of the other probable use cases of those narrow scale or smaller models. They will probably still be used on edge devices or on smartphones because they use lower computation, they require lower computation, they require lower RAM and everything because of the lower number of the parameters. But I think that will also pass, and these foundational models will probably get smaller, or the compute and hardware will be much better, but and also much cheaper in a few years,
Yeah.
depending on the Moore's law and everything that we once talked about but lost it
Uh,
in the previous meeting. Yeah,
I'm also very
and
Yeah, I'm also very pessimistic about whether or not edge devices could be a place for narrow models. I mean, the day that I saw Whisper is working so fine on an iPhone, I thought that, all right, this game is over too. So probably all these generative models will be soon small enough to fit
yeah,
on the processors of these mobile phones. So not quite sure if
yeah, and
any use cases.
yeah. And you're seeing this trend of quantizations and lots of libraries that help with quantizing these big LLMs and these parameter efficient fine tunings like LoRa and QLoRa. And people and researchers, I think, are finding their their works, their new kind of topics in just making these huge models available to most of the people that don't have access to those huge clusters. And also, I wanted to also mention the importance of these software engineering skills and also the problem solving that you mentioned. That these days, developers have access to lots of good models. The question is how you can solve the problem having access to these ingredients. It's like cooking or recipe, making it the recipe. So, yeah. And it requires learning lots of new things, being updated to the research and also to the APIs that these big companies are updating and releasing. So it never comes to an end. You're just learning so much, everything every day, and yeah, it is really stressful to be in this field at the moment.
Yeah, and you actually reminded me of a discussion that you and I had offline the other night regarding the importance of domain expertise. It's interesting because some of us, like you and I, we come from a medical background and we kind of jumped out of the world of medicine to learn about AI. And I guess now as we get more and more closer to the era of these foundation models, we might need to go a little bit back in, try to learn the nuances of our personal domains like medicine, for example, radiology for me, or whatever specialty we're going to have in future, and then try to understand the problems that are currently there, what are the pain points, and then maybe because now we know about these solutions, can basically tailor those solutions towards these problems. But that, I believe, kind of depends on how much you know the domain that you're working on. That's also important. So Moin, for the sake
Yeah,
of time,
definitely.
you mentioned something about LoRa and QLoRa, and I know that you recently ran into some interesting blog post about quantization. Is that one of the things that you're going to talk about today? Do you have that?
Yeah, I can mention that I haven't gone through that in depth,
If
but
if
this
I'm
is
not throwing
of
you off
course
your track,
it actually wasn't on my list to talk about, but let me see if I can find the link
if you have it,
quickly here.
if you don't, we can just
Yes, yes, I just found it. Yeah.
link in the comment. But
Um,
quite interesting when you shared that earlier. I just wanted to ask you about it. So if you have time to talk about it, because now you brought up the matter of quantization, I guess that would be something I can learn from you and everybody else.
sure, but I will probably stay at just introducing this blog
Yeah,
post I just found
sure.
out today.
That's
It's
enough.
a visual guide to quantization
Hmm.
and how different kind of methods could be used to represent numbers, like
Mhm.
the probably the most common or the default is floating point 32, but we are seeing even training of those adapters, those LoRa, actually QLoRa, even in integer with 4 points of precision, which is really a huge compressing of information and helps a lot in training it and making it accessible on consumer level GPUs. And this morning I was able to train a 7 billion parameter model on a 16 gigabyte GPU on
Wow.
Colab actually, which is crazy actually. Of course, I wasn't fine tuning every parameter in
Yeah.
there. These LoRa and QLoRa work, add some adapters that
Mhm.
are new weight matrices that add to these between the layers, and they only retrain those. But it actually works as a way of fine tuning the model. And this blog post really caught my eye because of the great visualizations of these floating point um, systems.
Nice.
And this is something that really needs some visual explanation
Yeah.
to help you understand it. Because, I mean, for someone like me who doesn't have a computer science background in academia, many of these topics were new, and I was just learning by seeing them and how the systems work. And they go down into explaining how this compressing of information from a higher range to a lower range, from
Mhm.
like floating point 32 to integer 8 works. And it really helps to understand how these libraries like bits and bytes that I think you've heard of in this is an extension of the
Yeah.
Hugging Face, how these packages work, how the weights are handled, how the activations and backpropagation is handled when training this. So I think this is a very good introductory resource to just learn about quantization. And then after that, I think it would be nice to just go through some of the blog posts by the Bits and Bytes team
Mhm.
to just learn how their library works, how QLoRa works, and also the QLoRa paper is a great resource. So yeah, that was it.
Perfect. Thank you. Sorry that I threw you off guard, but basically this was quite interesting and the figures do look good. So I'm going to definitely take a look at this one. Thank you.
Yeah,
Yeah.
me as well.
So let's go back
So,
to your screen. What else do you have cooking?
oh, let's see. I can go to this
Yeah. Total.
total segmenter annotate. Yeah.
Yeah, let's do it.
This is a great project. You can still see my
I
screen,
do.
yes,
Yeah.
because I
Yep, yep.
just made it full screen and
Yes,
sometimes it
yes,
doesn't
yes.
work.
No worries.
Um, this is a mm, online annotation tool introduced by the Total Segmenter team that published 2 papers on their model that I'm going to introduce in a bit. And this platform website allows people with different backgrounds, hopefully medical backgrounds, to just come and fine tune the initial segmentations that are automatically done. And based on the number of annotations that each of the researchers people provide to their team for the research, they come up with a cool kind of reward. And that is they give them access to some of their data. And I mean, based on their participation. So if the people and researcher come and do 10 annotations for them on their CT scans and MRIs, they give them the access to 100 subjects, and then with more effort they get more. And the cool thing was that if they do 500 annotations, they will be added as a co-author to the paper, which I think is a pretty
Yeah.
interesting way of yeah, involving people
Mhm.
in doing and crowdsourcing this annotation process. And I hope other teams start doing things like this. And I think this makes a lot of um, private medical data sets available to many people. And then the research projects that could be done on those data would be much, a lot more valuable. And also a few words on what TotalSegmentor was and how it started. Um, they started with a model. I mean, the goal was to provide a kind of like a foundational model. They weren't calling those foundation models at those days, but they wanted to make a pre-trained model for CT scan that could segment most of the important organs in the body and some other tissues, and also I think some vessels. And they came up with this TotalSegmentor model that was a big, relatively big unit that was trained on lots of, I don't remember the exact scale of the data set, but it was a huge data set of CT scans. And the way that they came up with the annotations for those first papers for TotalSegmentor was also cool. I remember that they first annotated only 10 CT scans or something, and then they trained their model on this very small number of cases. I mean, just 10 cases, and the model probably won't learn many useful things. But they started this way and then used this not so good model to actually provide labels or initial masks for the rest of the data. And then they started off those initial masks and fine-tune them so that it takes less time compared to when the annotator starts from zero and annotates every organ by hand
Yeah.
uh, without no help from the such an initial model. And then they repeated this loop a few times until every case in their data set was annotated. And then they, once after all of this data was ready, they trained the units on all of these data sets and then made it public as a tool for researchers. And I think it's an available extension for the 3D Slicer software as well. So it can help researchers um, start their annotation projects much more easily with these initial masks. And then they came up with the TotalSegmentor for MRI data. And the second model also worked well on CT scans. So it was kind of like a um, two modality, if you think of CT scan MRI as two modalities, model. And I think this is their third project. And yeah, I think there are good papers to read actually on how these projects get done in the academia and industry, how those huge data sets get annotated in the first place. And then there are lots of good details on how they develop the model. So I think this is a good resource, and I really like to share their initiative here and spread the word about this kind of crowdsourcing
Yeah.
AI projects and also medical projects that make it really hard to share data. And I think their work is very valuable. Anything you wanted to mention
No.
here? Yeah.
So this sounds a very interesting approach to crowdsourcing, a very innovative one indeed. And as you mentioned, TotalSegmentor has been a game changer in the world of AI and labeling data for segmentation. So I guess we should give them credit for basically implementing active learning and using weekly supervised training in a way that nobody else, at least in the world of AI, in the world of medicine, had done it before. They did that in such a scale and good quality that basically their models, were used by many labs, were adopted by many labs, very researchers, and I think still a lot of people use those. If I'm not wrong, I guess those are available through Moein as well. And Moein is a nice segment, and Moein is a nice library for developing deep learning using medical libraries or medical data. So basically, their models are great, and the way that now they are keep doing what they have been doing very nicely before is also very innovative. So lots of things to learn from their amazing work.
Yeah, and yeah, and just on my side, there are a few more resources that I'm going shortly to
Sure.
introduce, and
Yeah,
then I will hand it one last time to you.
sure.
And okay, let me just introduce some resources here. Um, okay, this is a good course with lots of high-profile speakers
Yeah.
on LLMs and agents.
Yeah.
And you can see the topics here. They start from the foundations of LLMs and then reasoning, planning, tool use, LLM agent infrastructure. There's a whole session on RAG, retrieval augmentation generation, and um, um, mostly anything that is important in the field at the moment. And this is the 2024 version, which all the videos and the slides are available here. And there's also an upcoming version for the spring of 2025, which people can go and sign up, I think for free, if I'm not mistaken.
Okay.
This was one of the resources. Then I saw another blog post by Sebastian Rashka, a great author and educator in AI, and he provided a list of the noteworthy AI research papers of 2024. Most of them are LLM papers, probably because of his interest in the field. But I think this is a very good list of good papers that came out in 2024 to understand the field and the scene of AI at the moment. So this was another one, and I want to mention once again that these links will be provided in the caption of the video and whatever way we can to the audience. Then another one, these were posts of kind of like the end of the year posts of different institutions. This one is from Latent Space, and this is the 2025 AI Engineer Reading List. They actually provide a list of different categories for AI engineers who want to enter the field to know what are the most important works at the moment that they need to know about in each of the different sections of AI, basically. And they provide 50 kind of papers. And also, I think there are lots of blog posts and other sources of other types of materials in there. But there are 10 sections on frontier LLMs. Of course, LLMs, this has been one of the main trends for the last 2 or 3 years. And then the second section is on benchmarks and evals. It goes to prompting and chain of thought, the frameworks that help models to these LLMs actually to reduce the hallucination and plan better. And section 4 is on RAG, which is, I mean, really interesting that the topic that came out, I mean, with this name, we had similar concepts to RAG in computer science from many years ago, but retrieval augmentation generation is a really new concept, but this is a very important section of these days of AI that a whole separate section is assigned to it. And
Yeah.
then there's a whole section on agents, code generation, vision, and voice. I mean, we have one section for vision, another section for retrieval augmentation generation, and basically on image and video diffusion and fine tuning. So it covers the main topics. I might disagree with some of these categories that I think they should be maybe classified in another way, but that is not an issue here. And for each of these sections, there are lots of good links to papers and blog posts and lots of educational material that you can look, I mean, you can look at it as a kind of a Wikipedia for links that are relevant to each of these topics. And then, yeah,
Yeah.
this
So
goes on for, yeah.
Moein, this is a very interesting list. I actually went through it once and found many interesting papers. The only thing that I would like to mention is that they say it's 50 links. Unfortunately, it's many more. So basically, every
Mm,
single item that they have there has at least hyperlinks to 2 or 3 blog posts or papers. So it's certainly much more than 50. But again, I think all of those, or at least most of those, are worthwhile, to just go through them, skim them, and learn something from them. And it really is a 2025 reading list, even though I'm pretty much sure that very soon we will have many new papers coming out of 2025 that we should read as well. So this brings us to our everyday's conversation on how to find time to stay up to date, to stay abreast of all these new findings in AI. But anyways, I'm happy that the science of AI is advancing this fast and we have a chance to be watching that live.
Yeah, I think this kind of compilation of links and papers, most important papers, is what people can do best with the to help gather the most important data out of this huge wave of coming papers into the attention of people, actually, so that the newcomers are not overwhelmed. I mean, not newcomers, everyone actually in the field is overwhelmed by the pace of research that is being published every day. So I think these kind of lists really help um, the people who want to enter the field and don't know where to start. What are the most important topics to learn about? What are the important papers to read first that are still relevant to the field? Because there are lots of important papers, but they are not a priority these days. They will remain good papers, but when someone wants to start, they probably want to know more about LLMs or VLMs, not something published in 1950 or something.
Yeah.
And I think this is the best we can do to get updated and stay updated to the field. And I hope that more of these kind of lists will be available soon.
Yeah, definitely. Definitely. Thank you. Thank you for sharing these. These are great. So I guess it's my turn to maybe for the last time share my screen and share something with you. So this time I'm also going to very quickly just introduce the topic of two papers and then mostly talk about agents and introduce two paper on agents there because I guess this is going to be exciting. But let me first open my one of these papers and then we can go from there. So let me share my screen. Moin, please let me know if you're seeing the screen.
Yeah,
All
it is
right.
sure now.
Yeah, so I'm going to talk about two papers. One is this one, Titans, and maybe also let me open the other one here. The other one was the mean max paper, Scaling Foundation Models with Lightning Attention. So both of these papers, they came out, I believe, 2 or 3 days ago, one after the other. There was only 1 day difference between them again, and both of them caught attracted a lot of attention. One of them, Titans, some people are even claiming that this is the Transformer V2 model because it's coming out of Google and it's again talking about something very huge. I'm not going to cover these papers in depth, maybe just to share the idea because first of all, the math in these papers are far beyond my pay grade. I cannot talk about this math very easily, but I am looking for many of the nice YouTube videos that I always come out and simplify these things for us. But the big picture is this. So the first paper, Mean Max, I believe this one came 1 day earlier. And this is, I'm not sure if they are a separate company. I guess they are a separate company, but they basically talked about a specific kind of attention. And so the kind of issue that this paper focused on was that you know how as the context window for large language models gets longer and longer, we put more data into their prompts, they tend to become more forgetful. They forget about the new kind of the nuance in the prompt that they needed to know about when we asked them about a small detail in a very large corpus of text that they received as a prompt. They usually fail in providing adequate answers about that. And this even has a name, I guess, needle in a haystack problem for LLMs, and some data sets have grown around that. And people are trying to come up with better ways for mitigating this problem. And now this paper, Minimax, is basically introducing a new kind of attention layer. So what they're saying is that probably the reason for most of these kind of shortcomings in understanding, in interpreting large contexts in prompts are because of the kind of linear attention that most of the nowadays modern transformers have employed. And then they talk about this and they first of all, compare softmax attention with linear attention. And these two are the kind of attention layers that have been all over in place. And if you're not that familiar with attention, I guess we are a little bit short in time to introduce them comprehensively here, but basically they are math products between different, vectors and matrices. And the results of that are the magic bullet behind transformers, which make them capable of doing what we have seen all these transformer-based models have done in the past. So this basically gives them the entire power to attend to many, many concepts at the same time. The thing about softmax attention, linear attention, is that these attention layers are very expensive computationally. And now the way, I mean, as you see, the paper is full of math and they go through the linear attention and why it is a heavy kind of, basically operation to do. And then they talk about lightning attention. And I'm trying to find out the place that they first introduced that. And it's very interesting because, so let me just read one sentence for you. So this approach identifies the primary bottleneck in the computational efficiency of existing linear attention mechanisms, the slow calm sum operation inherent in causal language modeling. So basically, they just focus on one single operation that is done within the linear attention layer, which is the calm sum, and they say that, hey, this is the bottleneck. So let's get rid of this calm sum, and now we can come up with faster attention layers that basically enables us to attend to many, many more tokens in the input prompt. And as the results here is showing, as they provide more and more long context to this a specific model they have developed here, shown in this red plot here, it tends to be much less forgetful and more accurate in the tasks that they double check this model on. And you see that here on this chart, we see GPT-4o, Cloud 3.5, Sonnet. So basically they have a collection of best available models at the moment as the comparison, which I guess is a very important and valuable thing to do. So this is one paper to have an eye on. And very quickly regarding the second paper, this is the one Titans learning to memorize at test time. So this is very interesting. Again, very heavy in math coming out of Google, and a very long blog post. I know that I've already watched a couple of YouTube videos about that, but I don't feel confident to talk about math yet of this paper. But I can tell you the gist of this paper. So what they are doing here is that they are basically trying to incorporate a memory mechanism in transformer architectures during the test time. So they are enabling transformer models to attend to different things that happen as they are talking and as they are basically output generating in the real time, and then keep part of that they have generated or they have learned from the user as their memory. And then they can select what to keep in their memory and they can select what to get rid of. They even have incorporated a surprise mechanism, which is quite interesting. They have really looked at how humans' brain works, and how humans' brain keep track of the surprises that happens to us every day, and how we actually replace some of the old memories with new ones. And as we learn new things, probably some of the old memories will get wiped out. And they are trying to incorporate the same mechanism into transformers. So they talk about the different kind of memory types. They incorporate a long-term memory, they incorporate a short-term memory, and they incorporate a persistent memory, I believe, which is kind of a day-to-day memory. So they have three different types of memory, and they kind of incorporate that as a context, as a separate layer, and as different sorts of attention mechanisms. So this is, again, a long but very interesting papers in case that you are very much into the architectures of these transformers. And again, as it has come out, it was yesterday, I believe, that first it was published, and everybody is saying that this is probably the new transformer model. And if these models can scale, then they are going to replace the transformer architecture across all different LLMs and VLMs that we are seeing nowadays. So just wanted to quickly make note of these two papers. Again, something interesting for people who are more into the architectures of the models and are, more mass friendly than us. Moein, I pause
No,
here. Do you have anything to share about these two papers?
no, I just saw this paper, the Titans one, not the previous one. I hadn't seen that. And it was really interesting to me. And I mean, the part that most interested me was the idea that it was kind of like inspired by how the memory module in human brain works.
Yeah.
And these days, I'm really into these kind of ideas inspired by neuroscience of what is missing in deep learning now that is not missing in the human brain or the biological brain, actually.
Yeah.
And I think everyone is looking for these. missing modules, missing parts that could be inspired. And this paper could be one of them. And no one knows now.
Certainly, certainly. And you talked about that, and we named Ian LeCun initially in this video. And I guess one of the main theories that he has been advocating for, at least for the past 1 year, has been that, we need structures in deep learning that are more akin to humans' brain, and we need to have uh, modules that work like a cerebellum. We need to have modules that work like cortex. We need to have modules that look like our perceptory organs, like eyes and ears, and then a combination of all those together might finally help us achieve AGI rather than a single LLM that in that module could be only maybe one of the organs that in the on-language map he has depicted. So I think there are lots to learn from neuroscience for developing these newer architectures. And again, Titans was one of the most recent interesting ones that came out. All right, okay, so very quickly, I'm going to talk about two resources regarding agents. Uh, the first one is a blog post from Anthropic, and Anthropic, as you all know, is basically the team behind the cloud family of models, Cloud 3.5 Sonnet, Cloud Opus, Cloud Haiku, all those ones. And you know that this is a model that is basically mostly used for coding purposes, and so this team has been doing a decent job in not only producing models, but also uh, publishing blog posts like this that really advances the field. And this time, I guess 2 weeks ago, they put together a very nice blog post on agentic AI, and they talk about what is an agent, how is an agent different from a naive LLM, and what is an agentic workflow, what is a multi-agentic workflow, and things like that. So I guess if you are into agents, which I think we all should be, because everybody says that 2025 is going to be the year of agents, and there are many, many people working on agentic frameworks nowadays. So then this blog post might be a very good place to start and get yourself familiarized with what agents are and how they are different from the other kind of terminology we tend to use in the world of LLMs and VLMs. And this one is a good place to start. So just a quick things, some quick catches from this blog post. Again, a long and not very long blog post, but it's a very informative one. I went through this a couple of times. So I think this can be easily a reference for people who want to work on the world of agents. The first thing is that it certainly gives a very nice definition of agents. And, I think that the most important thing on this definition is that it defines agents as systems where LLMs dynamically direct their own processes and tool usage, maintaining control over how they accomplish tasks. And this is important. The difference between an LLM and an agent is that the LLM, yes, it can answer whatever question or query that you ask from it, and it can do whatever you ask from it to do as well. But the point is that most of the time you are drawing the line that it should walk on. You are telling it what exactly to do and not to do. Whereas agents have some degrees of autonomy. They can decide on their own what is the best way for achieving a specific goal. If they have access to some tools, they can decide what tool to use and what tool not to use. They might even have some memory, which brings us to the previous papers. But long story short, whenever you have an LLM, ask yourself, is that LLM making any decision within the task space that you have assigned that LLM to? If it is not making any decision, it simply is a worker that is doing the job that you ask it to do. It probably is not an agent. But if an agent, if an LLM is more autonomous in decision making, coming up with its own ways for solving a problem, then it could be an agent. And obviously, multiple agents together could form a multi-agentic framework. This is the first thing that I learned from this. And obviously, this blog post talks about workflows, which is, workflows, a combination of how one can use LLMs, but not agents for doing many, many tasks. And they are saying that, for maybe 90% of the use cases that people have nowadays, a workflow of LLMs is suffice. You do not need agents or workflows of agents or multi-agentic workflows to achieve what you want to do. So this discrimination between workflows and agents, I guess, is a very nice aspect of this blog post. The second thing which was a minor message, but a still important one for me, was how they describe the nowadays frameworks in multi-agentic AI and agentic AI. And if you have been interested in this, you probably know that nowadays we have lots of Python frameworks and packages from LangChain, Llama Index, Crew AI, I don't know, a lot of different packages out there that they all claim that they can provide you with adequate control over building the agents and deploying them. Yet when you go through them, most of them will give you the sense that you are not that much in control of the codes that are being run behind the scene, or as we are dealing with LLMs, and some of these are commercial and cost you some money. You are not that much in control in how much you are paying. So they're talking about that, and this was the first official blog post that I saw talked about this, that hey, for most of the use cases, you can just code your agents yourself. You do not need to use this kind of frameworks. And I guess that's a message that really touched my heart, and I believe everybody else who's doing that would probably find some relationship with this advice as well. So again, a very nice blog post to go through. And I know, Moin, that you have some other blog posts similar to this one to introduce. But if you don't mind, maybe I quickly go forward and introduce another resource for this, and then I will pause and for the last time pass the ball to you so that you can also talk about all these agents. Is that okay?
Yeah, definitely.
Sure. So the next one that I'm going to introduce is going to be another paper, and probably the last paper that I introduce here. And it's a very nice paper. I guess it's so not this one. I guess I accidentally opened that, but I guess I can also talk about that now that it's open. So yeah. So okay, just one paper for you to know. So this is a very nice review paper that came out. I found that today. It talks about multi-agent collaboration mechanisms, and it talks about how multi-agentic frameworks could be set up from different perspectives, and how you can have them collaborate with each other. Maybe they need to cooperate, maybe they need to compete, maybe they need to co-opt. And they talk about the different mechanisms that these agents could work with each other. Again, I opened that by accident. I didn't want to introduce it, but now that it's opened, I just decided to give you a sneak peek of what this paper is about. So, multi-agent collaboration mechanisms, a survey of LLMs. It's a nice review from Ireland that came out, and people, I guess, can learn a lot from that, from how people have actually put together multi-agent frameworks in different ways. So this one I quickly go out from, and this is the one that I wanted to talk about, the Agent Laboratory, using LLM agents as research assistants. And this is a very nice paper. So this paper came out of Johns Hopkins University. So came out of a very scientific lab for doing what a scientific lab does. The idea is quite simple. The idea is that, hey, what if we can have a collection of large language model-based agents that can do all the steps that somebody needs to do when they are doing an academic research project. An academic research project mostly starts from literature review, and then it goes to plan formulation, data collection and preparation, maybe running some experiments, interpreting the results, writing the report or the publication, and then finally refining that final report. So this is something that, most of us do when we are doing academic research. And now the question is what we do replicatable by AI agents or not? Because if it is, then this means that, now we can have AI that can create science, and that science could basically close the loop and be used for training more AI models. And they do a decent job. I really find this paper quite interesting. The thing is super easy, and the workflow of the laboratory is clear on this figure. So basically, things start with a human that just gives a simple task to the entire framework, right? Just imagine whatever task, come up with some experiments to test if this vaccine is going to work or not. And then all these roles that you see here, PhD student, ML engineer, whatever, paper solver, these are all either one agent or maybe a collection of agents. So for example, this PhD student could be an agent working with GPT-4o as an engine. This postdoc could be another LLM now working with GPT-4o mini as an engine. Things like that. So the PhD student does a literature review, another PhD student and a postdoc probably assesses that. Then they come up with a plan for something, an ML engineer and another engineer. I'm not sure what SW stands for here, but they basically prepare the data together based on that plan. And then they
It's software, probably software engineer.
Software,
Sorry to
yeah, that
interrupt.
makes sense. Probably software engineer. Yeah, and then they pass it to a team of I guess an ML engineer, and I believe uh, an ML engineer with access to some tools. So these Python is probably a representative of some tools that they have access to, and they come up with some codes, they run the code over that data, and then when the code is over, the results is out, and even the result could be reinforced using some reward models, and then the engineer could see the results, maybe try to come up with a better version of its code, or if the code looks satisfactory and the results look satisfactory enough, just pass it to the next phase, which is now the report generation phase. And again, another agent goes through the results, put together a report, and the report is converted to latex. Another agent, which is a processor, goes through that, maybe providing some feedback, and then this refinement process continues. And then finally, it comes up to a final agent that maybe drafts the final report. So it's kind of similar to what happens in a real lab, if you have ever worked in one. So people work with each other as a team, and they come up with an idea, they work through it, plan for it, collect some data, analyze the data, and then finally write the publication. So it's a very nice one. And the last paper that I want to share with you, the last basically table here, I guess was here. So this is a paper that this is a table that is basically sharing how good quality these kind of agent-based tasks look like in eyes of some human experts who actually did the research in their real life, right? So basically, they asked some human researchers to take a look at these papers. This entire workflow that was run by agents, and then come up with some scoring, maybe out of a Likert scale of 5, and say how good or bad it has been. And if you look at this, if you look at these scores, you see that most of the time, the scores are not that bad. So these are regarding specific research questions, I believe. And then you have the research type, and then you have the scores that the humans attributed or assigned to these different phases of or different qualities of these researchers, from experiment quality to report quality to usefulness of the entire research that the agents did. And what really caught my eyes here is that, I mean, not a big surprise, these scores are not great, they are not ideal, but they are not low either. I mean, if you look at them, the scores look more to be average rather than poor or low quality. And this itself is super promising because it clearly shows that as we go forward and as we come up with smarter LLMs and smarter models, these scores could go high as well. So we are not that far away from an era that you can just come up with a question and maybe task a crew of large language model based agents to go and do that entire research for you and come back, right? And this is something very interesting. Obviously, now they are pushing the boundaries of LLMs we have to its max, right? They're using O1 mini and O1 preview, which by the time that this paper came out, were the best models available to the public. And yeah, I mean, nowadays it would be expensive to use O1 preview for writing a paper for you. But if you do, then your paper is not going to be bad at all. It might not be perfect, but it's average to good quality. And it is something fascinating in my eyes. And again, you can look at the scores based on the different models used and the averages of those, which again, as I said, caught my eyes as how good it was. So very interesting paper with lots of analysis and sub-analysis if you are interested to go and read it. I mean, they talked about the costs that they needed to spend for different phases of the project. So you see that, for example, the entire literature review took about $0.12. Which is kind of interesting. I really imagined that to be higher with GPT-4o, but basically, I guess they didn't do a very in-depth literature review based on the cost at least. So, but again, the results and the evaluation, it is kind of innovative and very surprising. So this is also a good paper for those of you who might be interested in multi-agent workflows and maybe how to apply that to scientific world. And this is something to read about. Moin, that was the last
Yeah.
I had.
Very interesting papers, and of course, this last one. Uh, One of the things that came to my mind is that this way of evaluating papers or the outputs of these LLMs is a really near real world kind of scenario that actually human reviewers are reviewing it and they don't know how this paper is made.
Mhm.
And I think getting those scores from high quality venues like NeurIPS or other top AI conferences is really not trivial. I mean, this
Yeah.
is not something that I mean could be achieved easily. And the model is probably working as a at the level of a junior researcher or even better. and they will get better. I mean, the trend is clear.
Mhm.
The model are getting better, and many of the things that we are doing and we were doing are getting automated. And it's going to be a really interesting few years ahead. And I think no one can predict where the whole trend is going. And all we know is that the models are getting better, and lots of the things that we were used to do by hand are getting automated, which is, I think, great.
Yeah, I think it's great. I think it's great. And you actually reminded me of something that I forgot to mention. If I'm not wrong, I believe one way that they evaluated this last paper was that they basically submitted some of these papers that were generated purely by agents to Noor IPS conference so that real human experts could look at them without being biased about how these papers were generated. Which I guess, as you mentioned once to me, might not be a very ethical way of evaluating your work, but a very innovative one indeed. And if somebody completely blind to how the papers came into existence, gave you an average score, and you only used agents for creating your work. This means that, as you mentioned, the trend is super clear. We are fastly approaching an era that the science could be generated by AI itself, and this will close the loop. And this makes the future scary.
Yeah, yeah, definitely.
Yeah.
And okay, so how much time do you think we have left
I think we are kind
for?
of over. We are a little bit over. Do you have any more papers to go through?
No, maybe just I wanted to mention the agents paper,
Yeah,
the
let's do
agents
that.
blog
Yeah,
post.
yeah, sure, certainly. We have 5 or 6 minutes. Let's do that.
Okay. So, okay, to just complement
Yeah.
the let me see which one to share. Yeah, in the past few weeks or so, a lot of blog posts and papers came out for agents. And the most striking thing to me about all of this was how differently everything was talking about the same thing. And it actually showed everyone that at the moment, no one knows a unique definition of what agents are or what AI agents are at the moment. Everyone is providing different definitions, different kind of classifications of how how to define the agent, what is the tool, what is the function calling. This terminology is really immature at the moment, but it is a really new field. I mean, these LLM powered agents, not the agents at all, because in artificial intelligence mm, textbooks, classical textbooks of AI, uh, if you look at them, the agent term is mentioned many times. And so the concept of agent is not new, but how we define it based on this new era of LLM powered agents is a bit complicated these ways.
Sure.
This blog post came out of Hugging Face, and they introduced a new library, smolagents, which is a really lightweight library to build agents, and this is the accompanying blog post introducing it, and they introduce a very I think nice table that complements what you mentioned from the building effective agents from the Anthropic blog post.
Mhm.
And before that, it mentions that most of the time you don't need agents, you just need multiple calls to the LLM, which is not called the agent. And they define agents something like this. AI agents are programs where LLM outputs control the workflow.
Yeah.
So I think this is a very important distinction of how these agents get differentiated from multiple calls to LLMs and then aggregating the results of those calls. So this effect that when the LLM output controls or differ or changes something in the environment, then this is where you can call it an agent. Is a really important distinction. And here they present um, five levels of agency. And as the pipeline gets more complicated, they assign different names. When you call an LLM, like for example in the UI of ChatGPT or in Claude, they call it a simple processor, and LLM output has no impact on program flow. Of course, in those UIs you don't have any programs, but you can call those APIs programmatically and just show the user the result of that call. And this is the basic way that these APIs are being used. When the LLM output determines basic control flow, it actually works like an if statement in the code. They call it a router, and the code becomes something like this. If LLM decision is A, do something predefined related to that decision, and then if the answer is something else, do something different. And the next level is tool call, and this is where LLM output determines function execution. So you can define some functions in code, and then the LLM provides the arguments to the function and calls it, and actually runs it in the environment, and then returns the output. So this is a bit more complicated than just being an if statement. It probably needs to figure out what are the arguments, how to run it, and how to process the output of the function. And then when the LLM output controls iterations and program continuation, they call it a multi-step agent. And this is where you can imagine that you have a for loop, or a loop actually in the code happening. And the agent, the LLM itself determines when to stop and when the results are good enough to stop that loop. This is much more control over the program. I mean, this can go wrong and cost you a lot because there will be multiple calls to the API. So this is a much freer way to put these LLMs into work, but it's still limited compared to the next one, which is the most free way to use these LLMs. And then they call it the multi-agent. So the multi-agent, you can call a program, a framework, multi-agent when one agentic workflow can start another agentic workflow. So this is beyond just a for loop of different LLM calls and then determining when to stop. This is where an LLM can start a whole process of LLM calls with another agent. So this can install lots of parallel agents and lots of parallel calls to these APIs, or just the inference pipeline. So this also provides lots of power to do crazy things, and this is the freer version of how these agents could be used. And this is the last level when they call it multi-agent. So
Yeah.
I really like how they classify this in terms of agency and control that and the control that model has. And they also introduced their uh, what do they call it? The small agents to
Yeah.
yeah, and how these agents work. They introduced the concept of code agents. So instead of just the in the traditional kind of way that these function callings were done, that the agent first produces the arguments, and then the arguments are given to the function in the environment, in the terminal, or in the a compiler that is being run in the environment. Um, they propose to do it differently with these code agents,
Mhm.
that the agent itself writes the code and runs the code in the environment. So instead of just outputting JSON files and then interpreting those JSON files and extracting data from it, the agent writes the code and tries to put multiple steps in just one code snippet
Yeah.
and do it much more directly. So this is how their library differs from the other agentic frameworks out there. And they say the writing actions in code rather than JSON like snippets provides better composability. You don't need to nest lots of JSONs into each other and then and then interpreting them to um, providing them to the interpreter. And also it helps with object management. So you can't put an image in the JSON, but
Mm.
you can generate an image in the code and then yeah, feed that image into another model in the code. So it makes it much more easier to work with these agents. And I think this is a very promising library because it's lightweight. It doesn't make it more difficult than it is to work with these agents. And there were also two other blog posts that I'm just going to introduce and not go into. One by Chip Huyen, the author of Designing Machine Learning Systems book, which is a great book actually in AI. She also goes through her definition, which is close to the other works, but still different classifications, different terminology being used. And also there was another blog post, yet another blog post by
Yeah.
Google, this agent's like white paper book
Mm,
slash
right.
paper. I'm not sure
Yeah.
how they're calling it, but it again introduces their definition of agents. What are the tools? What are the functions? What are the extensions? I think the word extension is being used in this paper, as far as I remember, a bit differently from the other two resources that we talked about. So these are other resources that who have that anyone who is interested in this field can dive into and learn more about how this field is getting its shape. And this is in the really early days, and I think this is normal to see these different terminologies and definitions for these agentic workflows.
Yeah, but I guess as we go forward, most of these terminologies will converge to kind of consensus on what we should call agents and what we should call agentic workflows. And I guess nowadays most of those at least have this agreement that, an agent should have some degree of autonomy. And, if they are not autonomous, then the problem is that they are probably not agents. So I guess we're getting there, and most of these white papers and blog posts are just setting the scene. And I guess this kind of signals how agents are gonna be bold in 2025 because the year started with these blog posts just preparing everybody with what is going to come next. Anyways, so
Yeah.
thank you very much. Thank you very much, Moein. So again, like every time that we talked before, I enjoyed this one as well. And again, this was the first time that we were recording this, so I really hope that people who watch this also found that useful. Please provide us with your comments, feedback. Again, please bear with us a little bit. This is the first time that we did that, in case that there were anything that you wanted us to change and you wanted us to modify in our workflow, please feel free to share that with us. Otherwise, Moin and I are mostly doing this for the sake of staying abreast of AI upcomings ourselves, and then we would also be happy to share it with you. So looking forward to see you again very soon, and looking forward to chat with you, Moin, very soon as well. Take care.
Yeah, and thank you. And I really enjoyed it, and I hope we just do it the same in a few next days. Yeah.
Perfect. Thank you.